This is the first, this is start of chapter 2 in Turbomachines. Now, this chapter is a prelude to some chapters that will be following. Turbomachines is a background topic we're going to be looking at in order to be able to have a basic understanding of how turbines work and compressors and pumps also, in order to prep for chapters that will cover hydroelectric power and wind power. In addition, this is also used in combustion turbines. So this chapter is not going to go in great depth into this topic, but we are going to cover the basics and go over some problems. So turbomachinery. What is a turbomachine? A definition of a turbomachine is a device in which energy is transferred either to or from a continuously flowing fluid by the action of one or more moving blades. So this could be for compressors or pumps, as well as turbines. So they can be classified in mainly, not exclusively, but mainly into three categories. So we have radial flow turbines, which basically means is that, excuse me, the fluid comes into contact with the turbine blades in a direction that is perpendicular to the axis of rotation of the turbine, or in a radial direction of the turbine. So then the fluid comes in, it makes contact with the turbine blades, and then it gets directed out in the axial direction after it exits the turbine. The axial flow turbine is you have the fluid again coming in the radial direction, but what happens is that the fluid is redirected into the axial direction, and then it makes contact with the turbine blade. So in the radial flow turbine, you have the fluid making contact with the turbine blades in the radial direction, but here the fluid is redirected in the axial direction before it makes contact with the turbine blades. Then, of course, you have what's called mixed flow, which means that the fluid makes contact with the blades in a direction that is a combination of both the axial and radial direction. So when looking into an analysis of a turbine or a turbomachine, a turbine or a pump slash compressor, we're going to go ahead and break it up into the various velocity components. So here's a diagram. I know it looks a little confusing at first because it's a two-dimensional surface where we're trying to look at a three-dimensional diagram. But if we look at the basics of this, what we're looking at are two things. We want to look at the absolute velocity vector of the fluid entering and the absolute velocity vector of the fluid exiting. So here, let's consider this our turbo machine, right? We're going to represent it in the form of a disk that has a certain angular velocity. The fluid is entering the turbo machine in a certain absolute direction, and that can be split up right into three directional components. And then the fluid is exiting at another point of the turbo machine, right? That's the absolute velocity of the fluid exiting the turbo machine. Again, you can split that up into three axial components. So if we were to go ahead and take this spinning axis, right? And if we were to take that and redraw a diagram here, where this axis is, this is again the z-axis, which is the axis of rotation. And if we were to take these absolute velocities and split them up into the three directions, it would be the following. You would get what would be called the axial component direction of the absolute velocity, the tangential, which is tangent to the rotating axes of the turbo machine, and then the radial direction. So then the absolute velocity itself would be split up into those three components. Now, again, let's make sure that we're all on the same page here. This is the absolute velocity of the fluid entering or leaving the turbo machinery, right? It's not always going to be exactly in a radial direction or always exactly in one direction. But what we're looking at is that our interest, right, our final interest in a turbo machine is the moment about the z-axis, or the moment about this spinning axis, right? What's happening, for example, a turbine is that a fluid is entering and leaving and causing the turbine to spin, or a pump is trying to spin to cause an increase in energy to the fluid. But in any case, what's of interest to us is the component of the velocity that causes the moment about the z-axis. So if we look at that, right, if we take the cross product of the radius to the absolute velocity of the fluid, we can go ahead and we can do our cross product matrix here. Again, I'm not going to be asking you guys to do this all on your own, but if I were to go ahead and split this up, right, if I take the, sorry, that should be a form of a matrix. So if I do this, right, I have my directional components, ijk, my velocity split up into the three components. I'm taking a cross product about the radius. I would get the following. Right, where this component is considered rotation, and this component is what we would call the only component about the z-axis. So what does that mean? That means that we can use that to find the total moment summation about the axis of rotation of the turbomachine at steady state, and that would give us the torque. Right, so if we take the mass flow rate and we go ahead and we multiply it by basically the difference between the rotation caused by the entering fluid subtracting out the exiting fluid, right? And then this number can be used to discern whether we're looking at a pump or a turbine, right? Again, a turbo machine can be a pump or a turbine here. So basically what we're looking at is if the product at the exit, or yeah, if R2 VU2 is greater than it at 1, what we have is that the exiting fluid has more energy than the entering fluid. So this is a pump, or basically a negative torque. But if it's the opposite, where the exiting fluids, basically the rotation of the exiting fluid, that energy or that moment is less than the entering, what happens is that now we're extracting energy from the fluid, and we end up with a turbine, right? So again, that's basically looking at the rotation caused by the fluid entering or exiting. So with that torque, though, excuse me, with that torque, we can go ahead and we can compute the power, right? So basically, if you remember, I think you may have covered this in dynamics, you get the torque multiplied by the angular velocity, and we end up with power. So if we take mass flow rate, and if we were to go ahead and basically bring in angular velocity into the torque equation, we would end up with the following. Now, we can simplify this further, knowing that omega r is actually going to be the tangential velocity of the rotor or the turbo machine at the entering point of the fluid, and omega r2 is going to be the tangential velocity of the turbo machine at the exiting point of the fluid. So then what we get is a correlation for power as mass flow rate multiplied by an equation that is a function of the product of the tangential velocity of the rotor times the tangential velocity of the fluid entering minus the same thing leaving. And if I go ahead and I take the power and I divide it by the mass flow rate, you get what's called the head. Again, where VU is the tangential velocity of the fluid, U is the tangential velocity of the rotor. Rotor and turbomachine and are interchangeable terms. Okay. So let's go ahead into splitting up here, introducing some more terms. So here we have the velocity, the absolute velocity of the fluid, right? Entering or leaving, that is the absolute velocity of the fluid. So we have here some arbitrary direction for the absolute velocity of the fluid. And here we have the tangential velocity of the rotor. This VR is defined as the relative velocity between the fluid and the rotor. And these two angles represent two different things. Alpha represents what's called the nozzle angle, right? The nozzle angle, the component that sets the angle, the velocity, the angle of the fluid entering. And then beta, this angle, which is the angle between the relative velocity and the tangential velocity of the rotor, is called the blade angle. So if you were to do some math with, recall the line of cosines, or the law of cosines, sorry, you would end up with being able to quantify the relative velocity of the entering fluid. You could do the same thing for it leaving. Bear with me, there's a reason why we're going through all this. With all of that, we can go ahead and recast an equation for the head, right? So the head, again, is going to be, I'm going to bring that equation back from the prior slide. And if we were to do some algebraic substitutions, we can actually go ahead and recast the equation for head. Okay, so we basically have this as a function of the absolute velocity of the fluid, tangential velocity of the rotor, and the relative velocity between the fluid and the rotor. This section, these two components here, would be regarded as the static effect, and this component here would be regarded as the dynamic effect, where we have the centrifugal force effect from the tangential velocity of the fluid, and then here again, of course, it's the relative effect between the fluid and the rotor. So then the question is why does that become useful, right? Well, there's this parameter called reaction, right? And it's a parameter used in turbomachinery, basically, which looks at the ratio of the static effect over the total change in head, right? Total change in head, which is representation of power. So if we were to compute this reaction, right, we would take the static effect from the head, right, the static effect, and we would divided by the total head. So if we go ahead and look at the static effect again, this is going to be a long equation. And that is the result of what the equation is for reaction. Now, why is reaction important, right? Well, we have reaction turbines and impulse turbines, basically, is how turbines are split, right? For example, if you compute this, right, and we get a reaction of 0, it means that the total change in head is due to dynamic effects, because here the static effect is 0. An example of that would be impulse turbines, right? Impulse turbines have a stationary nozzle that has a high velocity fluid that comes in and hits these turbine blades. They're not really turbine blades, they're called buckets, which causes this turbine to spin. That would be the result of a reaction of 0, because now all of the energy has to do with dynamic effects. Whereas if you have a axial flow device, right? So here's an axial turbine. Let's look at the specifics of an axial turbine as an example, right? So we have here entering fluid. So the entering fluid enters at the same radius that it exits at, right? I mean, here you have the fluid just kind of runs through the rotor in a direction that is parallel with the axis of rotation. In that case, too, the tangential velocity of the rotor at the exit point and the entrance and exit point is the same. It means the absolute velocity to the fluid entering and leaving is the same. So basically what happens is that our equations get modified because we're able to simplify them a little bit more. So for example, our torque, right? We would be able to factor out the torque. We're able to factor out the radius because it's the same entering and leaving, which again, for power, right, our tangential velocity is the same exiting and leaving. The tangential, velocity of the rotor is the same entering and leaving, which of course has an effect on how we quantify head. And then finally, when we compute the reaction for this, we only end up with the relative component of the reaction. Okay, that ends the video, the part 1 of chapter 2. The next video will be launching into an example problem relative to this. Thank you.